When you were a calculus student learning about infinite series, your teacher probably showed you the ratio test and the root test. And if your teacher was like most calc teachers, they didn't really explain why it worked, and they certainly didn't prove it either. If you took real analysis, then you probably saw a proof of these two theorems, and if you were anything like most students, that proof didn't really do much to get you to understand why the tests work. It just seemed like a bunch of epsilons and big N's. It turns out that the intuition behind these two tests is pretty simple, and in this video we will give you that intuitive understanding. As a bonus, the intuition leads pretty directly to an actual proof complete with epsilons and big N's. Don't worry if you find limit proofs confusing. We will do our best to make the transition from intuition to proof a smooth one. As yet another bonus, it will become clear that both tests can even be strengthened. That is, both tests can actually work in certain situations that your calc teacher didn't tell you about. And as a final bonus, we'll show you that one of the tests is actually better than the other. Well, sort of. More on that later. Here's the version of the ratio test that you probably learned in calculus class. Start with a series of non-zero terms we will call a sub n. We need them to be non-zero just so that we can compute ratios, but that's no problem because if our original series has terms that are zero, then we can just drop those terms. Now compute the absolute value of the ratio of successive terms. Now suppose this new sequence has a limit. If the limit is strictly less than 1, then the original series converges. If the limit is strictly greater than 1, the series diverges. Note that if the limit is exactly 1, or if the limit does not exist, then we get no information from this test. Here's a quick example. Let's take the sum of n plus 1 squared over n factorial. The presence of a factorial is a strong hint to use the ratio test. So we compute the absolute value of the ratio of successive terms, that is the absolute value of a sub n plus 1 over a sub n, which gives us, after some cancellation, a quadratic divided by a cubic, and you can use L'Hopital's rule to show that this approaches 0. So the original series converges. Now to understand why the ratio test works, we need a couple of prerequisites. The first is the comparison test. If we start with a convergent series of positive terms, and we consider a second series whose terms are smaller in absolute value, then that smaller series also converges. Next, we need to know when a geometric series converges. This type of series follows the rule that you multiply by a constant to go from one term to the next. In this example, we started with 1, and we multiplied by a half to go from one term to the next. And this particular series sums to the number 2. In general, if we call the first term a and the multiplier r, then we get convergence if and only if the absolute value of r is strictly less than 1. We don't need the formula for the sum, but we have a YouTube short giving a really cool explanation of the standard formula. We'll leave a link in the description. Notice that this already looks a lot like the ratio test. If someone gives you a geometric series, you can just take the absolute value of the ratio of successive terms and see if it's greater than or less than 1. The big picture here, which will soon become clear, is that if a series passes the ratio test, then this tells us that our series will eventually be dominated by a geometric series that converges. Okay, now the last prerequisite is one of the simplest and most intuitive tests. For a series to converge, the terms must have a limit of 0. In other words, if the limit of the terms isn't 0, you have a divergent series. Remember, this theorem only works in one direction. If the terms do approach 0, that tells you nothing about the convergence or divergence of the series. We're going to explain the intuition behind the ratio test, but to keep things concrete, we'll use actual numbers. Imagine that the ratio of successive terms approaches 0.8. That's smaller in magnitude than 1, but why does that give us convergence? If the limit is 0.8, then intuitively, this means that we can pick a really small epsilon, and the sequence of ratios will eventually get within epsilon of 0.8, and it will stay within that range. So let's pick 0.1 for our epsilon. This means that our sequence eventually gets confined to the interval 0.7 to 0.9. I said eventually, but let's make it even more concrete. Let's say that starting with the 100th term, all the terms of our sequence of ratios are in the range 0.7 to 0.9. Now the 100th term of our sequence is the absolute value of x sub 101 over x sub 100. Let's give x sub 100 the name a. Remember, that's the 100th term of our original series. It doesn't matter if it's negative or positive, so let's just say it's positive in order to keep things simple. What can we say about the magnitude of x sub 101? Well, we know the ratio of x sub 101 to x sub 100 is at most 0.9, So that means the magnitude of x sub 101 is at most a times 0.9. This works because we have a cap on how big the ratio of successive terms can be. We actually don't care that the ratio is at least 0.7. What we care about is that it's always less than 0.9. So the 101st term is at most a times 0.9 in absolute value. What about the 102nd term? Well, it can't be bigger than 0.9 times its previous term, because again, we have a cap of 0.9 on the ratio of successive terms. So x sub 102 is at most a times 0.9 squared in absolute value. And the 103rd term is at most a times 0.9 cubed in absolute value. To put it another way, I have no idea what goes on for terms 1 through 99, but the series that starts with x sub 100 is dominated by a convergent geometric series. The first term is just a, the second term is at most a times 0.9, the next term is at most a times 0.9 squared, and so on. So by the comparison test, the series starting with x sub 100 converges. And of course, this means that the entire series converges. Now let's quickly run through the case where our limit is greater than 1. To keep things concrete again, let's suppose that our limit of ratios is 1.5. Letting epsilon equal 0.1, we can conclude that from some point forward, the ratio of successive terms will be between 1.4 and 1.6. So at some point, one of the terms of our series is at least 40% bigger than the previous term, the term after that is 40% bigger than that term, and so on. In other words, our terms are getting bigger instead of smaller. And we know from the zero test that if the terms of the series don't approach 0, we have a divergent series. And that's it. That's the intuition into why the ratio test works. The best part is that this intuitive explanation translates very nicely into an actual proof, complete with epsilons and big N's. And now that you understand the why of the ratio test, the proof will actually make sense to you. We'll go over the proof in our next video. Speaking of which, make sure you subscribe so that you're notified when new videos come out. And if you hit the like button, then that greatly helps us produce more videos like this. Thanks for watching.